Yeah, I'm going to talk a little bit about how we manage air traffic in the future and how we're demonstrating that through small drones today. Right? As you think about what I'm showing up on screen, think about how this may apply to urban air mobility, high E operations, even space traffic management. Keep that in the back of your mind as I talk through how we manage small drones. I'm really appreciative to be here today. I know that this is kind of a new audience for me. Usually we're talking at other venues. I'm learning a lot, especially about my wardrobe. I'm sitting at the solid color shirt, jacket, no tie. Maybe that's why I'm still a civil servant, but see how this goes. Here we go. So I have a couple of wordy slides at the beginning, then I'll get a little more interesting as we go through. I don't think I have to impress you guys with the expected explosion of small UAS activity that's expected in the near future. There's a forecast from the FAA that talks about having 2.4 million hobbyists, 450,000 commercial operations by 2022. They keep revising these estimates, but they're all very high every time they do the revision. There's already over 1 million registered UAS operators. Vehicles are highly automated now. Airspace integration is necessary. These are new entrants to the airspace, right? These are not traditional aviation companies. These are not traditional operators. And they demand kind of flexibility for their operations and for speed of access to the airspace. But at the same time, everyone has safety on their mind. So how do we keep these operations safe and integrate them into the environment? Really, there's no tools, procedures, rules to kind of handle this at the moment. So that's really what our research at NASA has been about. How do we define this problem? How do we come up with solutions for it? How do we build a coalition around a solution that makes sense, that starts to enable these operations? So let me see if I can get to some of that. That brings us to UTM. So you've probably heard this phrase quite a bit. We heard it a lot this morning as well. It's UAS traffic management. It's really an ecosystem for small UAS in low altitude airspace. We talk about low altitude, we're talking about 400 feet and below. We talk about small UAS, we're talking about 55 pounds and under. It's amazing how many use cases open up just with those constraints, right? From delivery to infrastructure inspection, public safety, photography, videography. Lots of stuff opens up in this airspace if we can have these kind of operations. And the idea is that we want to enable industry's ability to supply services under the auspices of the FAA. It's still their airspace, right? It's their responsibility to keep it safe. But a lot of the services to enable the scale of operations we're thinking about can't be provided by today's system. So how do we make sure that we can enable these operations at scale in the near future? So our research is really about identifying services, roles, responsibilities, protocols, data models, safety levels, all kinds of stuff that we can offer as recommendations to industry and the FAA. We've done all this in partnership with government and the FAA along the way from the beginning, and we've learned a lot along the way, and I'll talk a little bit about it. One of the things with UTM, whenever we talk about it, it's important to realize that it's kind of like the story of a bunch of folks in a dark room and an elephant. And depending on which part of the elephant you happen to be fondling, you'll have a different idea of what that thing is, right? If you're feeling the leg, you might think it's a tree. If you're feeling the tail, you might think it's a rope. And the idea is that with UTM, if that's the elephant, depending on who you are, you'll have a different idea of what it is and what it should be. So really, NASA's role has been to try to make sure that we take into account all these different perspectives and come up with a system that makes sense for all the stakeholders. So we've tried to do a good job of that, and I'll talk about how we've gone about it. But it's a tricky problem to make sure that it meets everyone's needs. So the way we started is we got a bunch of stakeholders in a room for a couple of days, and this is what we came up with after a couple of days. These are really our high-level requirements. There were no requirements on UTM when we got started. No one knew what it was or what it should be when NASA started. And these 5-level core operating principles became our high-level requirements for building out the system. The first one on the left there is, wow, UTM, if it was a real thing, it should probably help make sure that drones don't hit each other. That would be a very nice feature of the system. Can it aid in that requirement? Next is, let's make sure that it doesn't hit manned aviation. Right? Let's keep those things separate as well. The third one in the middle there is related to some of the remote ID discussions you heard about this morning, and not having any anonymous flying in the airspace. All of the operators in the airspace need to be identifiable in some way. The fourth one is about common situational awareness. Data exchanges are going to be automated. They're going to be fast. They're going to be machine to machine. We want to make sure that they're well defined and everyone has the same understanding of the airspace and what they're seeing. The last one is to make sure that we have priority access to the airspace for operations that need it, so that the two hot dog delivery drones will get out of the way when the human kidney comes flying through, right? And it's pretty cool to think about. I used to use human brain as a joke, but now I use kidney because that's an actual operation use case that was tested a few months ago by GE on the East Coast. They actually flew a human kidney from a university to a hospital on a small drone, kind of illustrating some of the key use cases. And that was actually put into a person who is still alive right now, which is pretty amazing use case. So how did we go about testing this? Well, you heard from the FAA earlier today, you think about different requirements in different operating environments, right? So we started out small. This is kind of a crawl, walk, run approach. We started out in rural environments, line-of-sight operations. Back in 2015, we demonstrated this, right? So it feels like ages ago now. And it feels like it's not too groundbreaking to talk about it, but back then it really was. How can we share information amongst operators to keep the airspace safe in kind of this low-risk environment? Line-of-sight operation, not too many folks, not too many other operations in the environment. We moved up to TCL4 eventually, which we actually just finished testing, and that's full urban operations. So we kind of stepped our way up. So it's pretty cool to be able to say that, we flight tested all of these technical capability levels over the past 5 years, starting in August 2015 with our first flight test. Something I might not mention enough, especially as we rip through some of these slides and try and get to some questions, is that we did do this with partnerships, right? So every time we flew one of these TCLs, it was with partners who implemented the specification that they helped develop with us in collaboration, partnering with the FAA through a research transition team, trying to get our products to them as early and often as possible so they can do smart things with it, and making sure that we're feeding standards-defining organizations as well, so they can help definitively define the things that are going to define this airspace in the future. So it's a lot of partnerships that we had to develop to make sure we did this right. This is a slide from TCL3. So this is something we flew in 2018. But it's a really good picture that kind of talks about all the different elements that we like to test during our technical capability level demonstrations. So in TCL3, you'll notice on the top there we have a thing called FIMS and a thing called USS1 and USS2. FIMS is a flight information management system. You can think of that as a piece that the FAA may implement to support small UAS operations. USSs are software systems. They're UAS service suppliers. Those are things that actually allow operators to access the airspace and have their data shared amongst others in the airspace. So those USSs talk to each other given a specification. But then there's also a lot of vehicle technologies that we're testing out as well along the way. So vehicle-to-vehicle communications is stuff we looked at. We looked at different kind of avoidance, obstacle avoidance and for ground and air obstacles. Airborne radar, ground-based radar, redundant C2, augmented navigation. A lot of technologies we invited folks to show what they could do for these small drones and test them out in this test environment at the FAA test sites. So if you guys weren't aware, when we started there were 6 FAA test sites, there's now 7. And all of our testing was done there after TCL2. This is TCL4. We just completed this in August, so this is kind of hot off the presses kind of stuff. We tested at 2 of the test sites in Nevada and Texas, in Reno and Corpus Christi specifically. It was managed out of NASA Ames Research Center, which is here in the Bay Area for those that aren't familiar. So this is a Bay Area-based project for NASA. We looked at common nav, detect and avoid, large-scale contingency management, a lot of different aspects for TCL4 in those environments that you're looking at in those photos. That's where we actually flew multiple small drones simultaneously to get a sense of what the system needs to do. To prove it, look at those yellow dots. There's drones in there. So this is over downtown Reno. This is 4 drones flying simultaneously over downtown Reno. This is on the 18th of June. We flew in Nevada first, then we moved the show down to Texas, and we did similar stuff in Corpus Christi. So I wanted to talk briefly about what is UTM actually doing. We talked about it as this kind of nebulous concept, but if we think about it in terms of these operations you're looking at on the screen right now, really what we're doing is we're saying, let's imagine each of those operations, those 4 small drones, they each have a different mission. One is taking pictures of a cell tower. One of them's delivering, again, that hot dog. Another one's doing a public safety surveillance mission, whatever, right? They're all doing their own thing. The idea is that they would all be supported by a UAS service supplier. They would share their intent with their UAS service supplier. Each of those UAS service suppliers, let's say there's a different one for each of those drones, exchange that intent so that they're all aware of what's happening in the airspace or what's planned to happen in the airspace. If there's any known conflicts at a strategic time frame, they can negotiate those or replan around them. And then as they're actually operating, if anything dynamic comes up, they can communicate via these USSs what's going on, whether I have to make a contingency landing of some sort, or I need to change my plan for some reason. These are communicated from the operator to its USS, and then from that USS to the network of USSs, so that things can maintain as much safety as we can at that layer. And then these are supported by vehicle-level technologies, right? So that doesn't obviate the need for vehicle-based technologies for detect and avoid or redundant navigation or whatever else you might need. So there's multiple layers here to try and maintain safety, and that's what we're really trying to demonstrate and test out in the field. And that's what you see here at Reno. So as a project, it's really our goal to develop these concepts, show how they might work, formalize some APIs, maybe some specifications, maybe some requirements, some software testing approaches, and then feed those out to the right places, right? As I mentioned, we have a research transition team set up with the FAA such that we can not wait until the end and just throw over a boatload of data and documents and say, here you go, FAA, and we walk away. We've learned that's not a very productive way to do business with them, right? We work together very tightly. We can get a sense of where the FAA is heading regulatorily. We can let them know the kind of testing we're going to do. We can converge on productive things for folks along the way. Likewise, again, we partnered with industry. We got good buy-in from them on these concepts. We heard folks talk about remote ID earlier this morning and how it was successfully tested and demonstrated in Switzerland and California just last week. If you look at 5 or 6 of the participants in that demonstration, they're all graduates of NASA UTM, right? They're taking the concepts and the learnings of what they've seen in UTM, they're formalizing them, demonstrating them, getting buy-in from more folks. And that's really kind of the charter of NASA. We don't run operational systems, right? We come up with concepts, we test them out, we document them, we provide data. And based on that, you can see kind of the fingers of that propagating throughout the system, which is great to see for us. So a lot of activity right now in ASTM and RTCA related to some of the vehicle level stuff, or whether it's the USS to USS communication or remote identification. So we're really happy to see all of that. So I'm not too hard to find. Feel free to send me an email if there's anything I can follow up on. I wrote a few notes here to see if I can remember if I forgot anything. No, and I posed that question to you at the beginning, or that statement to you at the beginning. Think about what I'm talking about here and how it may apply to UAM, or if you're more interested in high E operations, above 60,000 feet, how these kind of concepts may apply there as well. And even in space traffic management, right? These are places where services aren't really provided by anybody, but there's folks that want to use these environments. So how do we come up with systems to allow them to exchange data, keep those airspaces safe, and still perform their missions? And a lot of the things we're learning in UTM can apply to those domains as well. With that, I think I'd be happy to take the last few minutes here with any questions.
Great. Do we have any questions for Joseph? I'm just checking Slido, sorry, quickly.
Sure.
Any questions? When do you think the US will have comprehensive UTM covering the whole of the continent?
Yeah, it's a good question. The first thing to realize is that we talk about UTM as a comprehensive system covering kind of all use cases and all aspects of small UAS activity. But really you should think about it as a collection of services. And these services over time will get rolled out. It was mentioned this morning, I think, by Ben at AirMap on the LANCE system, the Low Altitude Authorization Notification capability that the FAA rolled out. We were able to help out with the initial testing we had done in TCL1, understanding how you can exchange data digitally. They took that idea and ran and came up with LANCE, enabling more operations in the airspace, so that you can actually consider that an initial service, a UTM service of the airspace. Remote ID will be one of the next ones that will come out. And all of these are enabling more and more operations as we move forward. So it's not a monolithic system that gets turned on in 4 years or whatever it might be. It's additional services and additional capabilities, additional rules that allow more and more operations over time. So I think over the next 4 or 5 years, you'll see more and more use cases enabled by this rollout of services. I've got still 4 minutes. I could stand up here and stare at all of you.
Okay. What are some applicable lessons learned from your TCL4 testing that applies to above 400 feet where UAM operations will occur?
Yeah, it's a good question. There are quite a few, and we're formalizing them now. Again, we just finished flight testing last week, but some of the higher level ones we can realize is that simple stuff related to exchange of situational awareness amongst these airspace providers, these USSs, kind of the latency and complexity of those are not a barrier to operations, which is great to see, right? The latency of communications there at the strategic horizon does not impede actual operations. The things that impede operations right now are the onboard technologies, right? The things for detect and avoid and redundant navigation, a lot of EMI issues that folks don't have mapped out in cities very well, but know they exist. We experienced them directly in Corpus Christi, right? As you got closer to an apartment building, everyone's Wi-Fi routers turned on. Depending on what your C2 link was, there would be issues. Again, these are things that are known, but until you get out to illustrate them in the airspace, it really becomes concrete for folks to think about what it means to do those operations. So that's another one. Weather's always been an issue. I know PK mentioned it this morning on the panel. Getting further information about these small vehicles and how dependent they are on good weather information or reacting to weather appropriately. We know that the larger vehicles are larger and have different reactions to weather, but still there's a highlighted need for improved weather forecasting and weather measurement in the urban environment. Again, these are things that aren't groundbreaking, but when you can really solidify them with some numbers and measurements and observations of actual vehicles in the environment, it really helps to have that conversation. That's just a couple at a high level.
I have a quick question. So I know you mentioned onboard technologies limitations. What is the, maybe the top 2 or 3 items of onboard technologies that you really need to have working correctly before we can actually scale up and multiple aircraft in the skies as a practical solution? And if you have possible solutions, or at least what you're thinking of, that would be great to know.
Yeah, so whenever I speak like this, I am mostly speaking from my experience. I don't speak specifically for NASA as a whole as the definitive list, but I think some of the things that you have to think of with a question like that is, can you mitigate some of those lack of technologies in some other way, right? By having increased uncertainty buffers on time or space, you can mitigate some of the lack of nav precision or C2 reliability. Right, so actually finding out how to do a cost benefit on some of those trade-offs is really important, and that's one of the things we're trying to look at and highlight as well. But yeah, I think those are the big ones, or things that are like, another thing to think about is how you react to those problems occurring or those lack of reliable technologies to exist. So if you have appropriate responses to a loss of C2 or a loss of nav, then you can actually maybe not have as many nines of reliability on those capabilities. So I think it's about testing in the environment and figuring out the right questions to ask. And it's hard to do, and they don't really come out until you go out and actually fly, and you bring in a bunch of partners to the table. But if you just had to put a list of things, yeah, it is DAA, and it's redundant nav. It's the things that are known to be important in aviation that are not as well understood for the small drones in an urban environment.
Brilliant. Thank you very much. That's great. Thank you.